Okay, good morning, everybody. I graded the test, and I'm pretty impressed with this class. Most of you did a pretty good job. So the median, I haven't input all the score in the system, but based on the score I roughly look at, the average in the median is right about 80 to 82-ish. And some of you did a good job, almost get everything right. So I congrats for those who did a great job. And if you have any questions with this, feel free to reach back to me and we can review your test and go through with you. Otherwise, what we're going to do today is we're going to go through the test with everybody. I'll hand it back to you. But at the end of the class, I do want to get them back. So if you can drop off right there after the class, that will be great. If you have any concerns, let me know with the grading. It should take about 30 minutes or so. Then we will have some time to transit into the next chapter. So I'm going to start with Penelope. Good job. Kristen. I made arrow, so I adjust a little bit. That's the final, 87, okay?
Thank you.
Try. Nick.
I got 2 of them.
Right here. Oh, sorry about that. Chandler, I don't think he's here yet. David. Gyration. Ethan?
Yes.
Sorry. Ethan. Okay, we got Jeff. And we have Andrew. And another Andrew. Here you go. Good job. Parse. Anthony. I don't see Chantal here today either. Not yet, probably. Teresa. And Evan.
Chantal's here. She's not in here, but she's here.
Okay.
You want to put it where she sits?
Sure. When she comes in, I will hand to her. Well, I want to comment a couple things. Oh, please take a look. Take a minute or two to see how everything goes from the test. And then we will begin in next minutes or two, okay? I'll give everybody a little bit of time to digest a bit. This is a fairly straightforward test from my perspective, but we can chat more. So overview of today's test is this is trying to recapture what we taught in the classroom, mostly relevant to chain conformation, etc. So the multiple choice is, I think most of you did a pretty good job. The short answer is pretty good for everybody's understanding as well. So 11, 10, question number 10 and 11 relate to excluded volume. And cone length, I don't think many of you had any problem at all. Here you go, Jackie. Please try to be on time. The numerical question, I saw some of the problem. Most of them are relevant to, about half of you got question 12 right. It seems a bit confusion when we ask what is RG, only give you molecular weight, right? So some of you get this right, but I think quite some of you have the problem with it. I'll explain how to solve the problem 12. And problem 13, not a lot of confusion for A and B, but some of you had issues with C. That's a challenge, I think. I think the problem is when we ask everybody what's a chain conformation in SATA solvent. Some of you had some trouble distinguish between the SATA solvent and in the regular solvent, or in the considering the bond angle, etc. So we will go through that, C as well. 14 is a little bit challenging. The question is asked in a fancy way. Oh, Chantal, let me hand your test back to you as well. Here you go. We just started. So the question 14 is basically a fancy way to ask what is a contour length and what's the end-to-end distance when you have a chain span through a small pore, okay? But it doesn't differ too much with question 13 actually, from my perspective. Question 15 is some relevant to what we discussed in the class. I think a majority of you get this bonus question right. So now let's go by one, okay? Let's take a look at the question number 1. Consider a free joint chain with bond length of L equals to 8. If the mean square radius of gyration of this chain is 500, what's a segment? How many segments? So I think some of you, most of you get this right, but some of you choose B. And the issue with B is that you probably missed the end-to-end distance versus radius of gyration. Radius gyration is smaller than end-to-end distance, as you know. There is a factor of √6 there, and that's, some of you might miss it, so keeping in mind that's the difference. So question number 2, relevant to, for a semi-flexible polymer such as DNA, the most appropriate measurement of stiffness. For this one, I think almost everybody got this right. It's the persistence length is the best way to measure the chain stiffness. A is also possible, but it's not the direct way to measure stiffness, and it's less used because it's also influenced by the segment bond length L, okay? So combining characteristic ratio, bond length, and you can get the persistence length, which is a proper way to describe. Number 3 is ask you about what's the radius of gyration. It's give you all the parameters you need. So the calculation is fairly straightforward as well. You need to get the number of bonds based on monomer repeating units. You need to get the length of the bond. Then based on the same equation you used in question 1, you should be able to get the right, what is it called? You should be able to get the radius of gyration correct. So that is C if you got this right. And now question number 4, we actually go through in the homeworks. How does RG for free R end-to-end distance square for 3 different cases? random versus alternating versus die block. Since it's a free joint chain, so actually there's not much difference between those three. So the correct answer should be C, which is equivalent for all of the case. I don't think this one any of you had any problem. Next question is about cone length. As we know, cone length is relevant to persistent length. It's basically a direct way to measure the rigidity of the polymer, right? So when the cone length decreases, it's more relevant to the flexibility. So the chain is more flexible. And let's take a look at A. It says in more stretched conformation, not necessary, right? It's actually stretching is not relevant to the rigidity of the polymer. C, more sterically hindered. That's not the case either. Less flexible, it's counterintuitive with question B, right? So we know it's not correct. E, increase in molecular weight. This is a total nonsense. When we talk about cone length, there's nothing to do with molecular weight. More likely to give up. This is more also not particularly relevant. Okay, that's talking about we just need to fill a question F, so we write something not particularly relevant. We never talked about give up in polymer physics class, so or yield, etc. Okay, so now what the question thinks? What will happen if the chain its value for C infinity increases? So we have a few different answers. When C infinity increases, we know characteristic ratio raises up. You would expect to have a more rigid chain. So if the number of bonds and bond length is fixed, you would expect end-to-end distance to increase. So clearly, between A and B, A is the right answer. So regarding C, the bond angle will experience a great strain. At the first glance, this seems makes some sense, but the bond angle is not specified what is the value is. So is it given the strain restrict to high theta or low? It's not clear, so it's better to leave this C option out because it didn't say what the exact angle is. And E, the degree of permutation will increase. Again, your dp number of bonds has nothing to do with persistence length characteristic ratio. F is clearly not the option if you have A picked up there. So the next one is interesting. Some of you had a problem. What effect will a good solvent have on the radius of gyration of the polymer compared to its radius gyration of the melt? So what is the RG in good solvent? As we talked about, when you are in good solvent, you start to experience excluded volume. Compared to melt, which is equivalent to a theta solvent. So good solvent versus theta solvent, you will have increased radius gyration. Okay, and in one of the homework and example, we actually did an example talking about what is the radius gyration in for polystyrene in good solvent with the theta solvent, and we saw there is quite a, depending on molecular weight, you can have an increase up to 10% or up to 100% is also possible. So number 8 is a problem. I see quite some questions from this one. So read this carefully. So for a semi-flexible polymer, okay, that's one definition. With what power of n would Rg varies in the limit of contour length divided by persistence length much smaller than 1. So let's first take a look at the last part. What LC divided by LP much smaller than 1 means? That means your LP is much bigger than contour length, right? That's in the range of rigid rod limit. Okay, is it clear to everybody? So if this is behave like a rigid rod, how does Rg depends on molecular weight? It differs with flexible coil, right? So in the rod case, your molecular weight increase, your rod length increase linearly. So this indicates that E is the best answer, which indicates you would have a linear increase, okay? I saw some of the students had the question C or D, but if it's in the flexible polymer, it's not in the raw-like limit, but if we reverse LP divided by LC is much smaller than 1, then that's indicative of the answer of C, which is 1.5. But in this case, it's a raw limit, so the answer should be E. So number 9, which of following represents a quantitative definition of a Seder condition? We ask this question a little bit back and forth. Seder condition defines as when the polymer dissolves with solvents, when the polymer adopts a similar free joint chain model. So let's take a look at the first one. Standard deviation of end-to-end distance is 0, which is not the case, okay? The standard deviation has nothing to do with Seder condition. Same for B. A and B are basically the same wording, but they don't make much sense here. The chain expansion coefficient is 1. This is a good one because when your polymer is not expanding in good solvent, that's indicated of Seder solvent. D is not relevant as well. First derivative Rg by temperature equals to 0. Means the physical meaning is Rg is not temperature dependent. It's not a particular case here, okay? The solution temperature is larger than Tg. Again, this is not relevant, particular for here. So the correct answer should be C. The question 10 and 11 is pretty straightforward. I don't see much trouble from everybody. So we're going to quickly go through them. So explain what is meant by excluded volume. So a lot of you describe very nicely how excluded volume is relevant to self-avoiding work when your polymer is occupying the same space. Your real chain could not adopt the same space again. So in this scenario, when we consider this excluded volume, your scaling relationship between the end-to-end distance or Rg will be larger than n power of 0.5, which means there is a swallowing effect. I don't see much trouble for this particular one. So next one is interesting. I think a minority of you had some problem answering this one. How does cone length of a chain compare to the length of each bond of the backbone? So first, what is cone length? We need to understand. Cone length is relevant to persistence length. It's basically double the value of persistence length. And cone length is equal to characteristic ratio times the bond length, right? So here the cone length will likely be larger than bond length in most of semi-flexible polymer, and this is defined by what the characteristic ratio are, or what's the rigidity of the polymer. Okay, I'm not sure why some of you are confused. Maybe the cone length was not as well defined as persistence length in the classroom, but they are basically proportional, okay? Okay, so now the question 12 is, I didn't expect this one to be that hard, to be honest. So some of you go through really lengthy process to trying to illustrate the relationship between different parts, but they should not be that difficult, okay? So let's see. What is this? This asks GPC analysis of a batch of polymer made in the lab has revealed at present 2 fractions of the polymer. with identical composition, but a factor of 4 in average molecular weight. So we know they're the same material, right? From the same batch of the polymer. And why in GPC they come out differently is just because one has a higher molecular weight. It will have a shorter elution time. So it basically tells you the molecular weight differs by a factor of 4. If the lower molecular weight Rg is estimated to be 13 nanometer, what is the Rg of the higher molar mass portion? We also added that, assume the chain is in the Seda solvent here, just to help you a bit to save some time. So how do we approach this problem? This problem asks you what is the relationship between the Rg and molecular weight. So in terms of Seda solvent, Rg will be equals to NL squared divided by 6, Rg squared, okay, right? So in this case then, Rg will be equals to N power of 0.5 multiplied by L, right? Its scale with molecular weight power of 0.5. We don't need to know what the bond lengths are in this case, actually. We don't need to know bond angle, because this question basically asks you if we double the N, what the new Rg will be. And if you got it, the N, take a root square of N of 4 will be equals to 2. So some of you, I was a bit confused. I think when you're doing the math, you made some mistakes, so I took some of the points out. But it basically says you should take a root square of 4. We'll give you, the Rg will be scaled as twice of what the original Rg, which is 13. So if you use 13 multiplied by 2, that will give you the final radius of gyration for the higher molecular fraction, okay? So that should be equal to 26 if you got everything correct. Next question is question 13. We are asking you about what is the statistical segment length, persistence length, and radius gyration for a particular polymer. I would say 90% of you got question A and B right. This is quite closer to one of the homework we did, so I hope you get that. It's quite straightforward. If you need to calculate B square, you can do two ways. Either you can assume a molecular weight and then use that molecular weight to calculate what the B length, or many of you basically normalized the N versus the monomer molecular weight. So B squared should be equals to M. I can do a little bit of writing, so that helps everybody. Let's see. Not much color left. Let's pick. There's a little bit white. So this is a given. It asks you what is B value is, right? So, but we know MB squared will be equals to R squared. So use this relationship. We can actually plug in the R. So this will be equals to N. And you can apply molecular weight will be equals to number of repeating unit with repeating unit molecular weight. This is no, is 56, and this is no. So we can cancel out the N because they're the same. You can reach, this is pretty straightforward. I think 90% if you got this. If you got this correct, this is roughly 5 angstrom or so. In the next part, it asks you what is persistence length, and that could be a confusing part. So how do we get persistence length if we know, for example, B value? It's not that hard, right? So again, our end-to-end square will be equal to C infinity in L square. Number of bonds, bond length, characteristic ratio, and we can get characteristic ratio based on the MB square, and we can use LP equals to half of C infinity L to get to what the LP value is. If you guys need me to go a little bit detailed, I can show you what is it. But briefly speaking, we can get C infinity going to be equals to B squared, MB squared, and NL squared. So N and N, they have a certain relationship. In this case, N will be equals to, in each repeating unit, we have 2 bonds. So you can apply this here, and excuse me, I write it reversely. N will be equals to twice of degree of polymerization. There's more bonds, so in this case, you can write 2N L squared. The N will cancel each other. L is no, which is carbon-carbon bond. B is basically given by the last equation. So you should be able to get characteristic ratio about 5.8 or so. Okay? And use that value, you can get LP. LP will be somewhere around 5 angstrom. I know some of you get it close. Last part, C is a little bit deceptive when we ask the question. I understand you all get the point with the radius of gyration, how this is relevant to the bond length, number of bonds, etc. So how we approach this is we giving the molecular weight. We just need to use a molecular weight to get number of bonds, which is given by this particular equation. So N equals molecular weight divided by NW. So this will be equals to 5,056 multiplied by 2. So your N is about, if you get the M value, you can get RG squared. Average will be NL squared divided by 6. A lot of you added a characteristic ratio here, which is not necessary in this case because we specifically ask you for a theta solvent condition. Okay, so that's some of the confusion you have, and we take a little bit of point if you have the characteristic ratio here. So make sure when you do a calculation, you don't add this C infinity there. Okay. All right, pass it around. Enjoy. We get another box. So
Whoa.
nobody won then?
Let's calm down here. I went ahead and... Alright, so we keep the box, right?
You guys can keep it. That's what we promised for. Although we said only 6 of them get that right, but let's share everything. I'm glad the delivery guy didn't mess up. So called me. I got a notice. He's right out there. So last part. Feel free to enjoy it while I explain the last part. I'll let everybody get started, settle down, and we can continue, okay?
Take anything.
Why is it so hard to decide, folks?
It's a difficult part to decide. You should get all the same.
Mm-hmm.
Thank you.
All right, so while everybody start to settle down, let's talk about this part. When you get the contour lens, as I explained, you can get what the number of n is. You can use the n to get what the repeating unit part n is. Then you can understand what the molecular weight is, right? That's the rationale. Let me show you exactly how you need to do it. So if you get the value of 200 nanometer, which is we know, the bond length is 1.54 angstrom. Remember, we said this is assuming the chain is fully stretched out. No bond angle need to be considered. I need to add a 0 because this is angstrom, this is nanometer. So you can calculate a value what it is. Unfortunately, on my last year student answer, they didn't give the answer. But if you use a calculator to calculate what this value is, you can get n, right? If you use n divided by 2, you would be able to get the repeating unit. That's what the definition is. And the molecular weight will be equals to number of n multiplied by monomer molecular weight, which is 28. I don't have the exact answer on my sheet, so feel free to do a quick calculation. But that's how we get this. For the second part, we ask you, what is a polymer if it's actually to be flexible coil, if it can span the whole length. And that's where a little bit confusion is, because we give the bond angle and the bond length and statistical segment length. Some of you are confused by why we need so many information, especially we given the bond angle part. A lot of you are applying the free rotation chain model. That's fine, but remember we already gave you the statistical segment length. Why not just use RG square equals to MB square divided by 6? This is the most straightforward way to get a good answer. If you go through all the troubles, use the bond length, you should get similar values in B or C infinity. They are basically quite similar. Although you might have run into trouble because we didn't give you a phi angle. Okay. So basically, there is one uncertainty is, I think ambiguity is, we assume RG will be equals to when the polymer will be spanned over this. Okay, so let's assume that's the case. The diameter is 100, so RG just needs to be reaching 100 square. You get what the value B is. Right? B is given by 5.9 angstrom, so this couldn't be equals to 5.2 and 6. And I need to make one revision. This should be angstrom, so this will be 1,000. So you would have 1,000 divided by square. Okay, then you can get what m value is based on 6 milling divided by 5.9 square. You can get what the value is. And the molecular weight will be equals to n multiplied by n0, which is, this is given by 28, right? So you can get, the n should be, if you got everything right, molecular weight is fairly large. It's on the milling or bigger, okay? So that's what we're trying to do, is ask you how to get the value about how to get the end-to-end distance equal to a given pore length or versus a contour length. They're slightly different. In the bonus question, I think everybody more or less get this right. I don't need to go through it. The answer is all in the textbook about free joint chain, free rotation chain, etc. So that summarizes the questions and answers. Overall, I thought, oh, please.
How much was the bonus worth?
10 on the top of whatever. So some of you over 100%, so I assume that means you did a fantastic job. Any question for the test? If not, or if you have some question you want to chat with me privately, feel free to drop by my office as well. Otherwise, please.
Where do you get to 100 from 200?
That's a pore length. RG, we just need to consider half the diameter. If no more question, let's move on to the next part. I think we got 10-15 minutes. I'll give everybody a little bit overview what happens to the next. Okay? You guys can give it to me after the class. That's fine. So we did a pretty good job overall for the class to understand the conformation, length, etc., etc. So the next chapter, we're going to put some of what we learned into good use. A very big part of the good use is relevant to polymer solution. So we're going to start to talk about, first is review of what is entropy and enthalpy is, the thermodynamics, because that dictates how your polymer will interact with its environment. We will learn some of the reason why the small molecular are likely to mix very well. For example, if you pull a toluene versus a hexane or toluene versus a benzene, you shake it, the solvents like to mix intimately, okay? But for other material, let's say if you're putting a polyethylene versus a polystyrene, you heat up, you shake it, they may not want to get along. There's a great reason why one mix well, the other does not. So in the next chapter in polymer solution, our main goal is to understand what is the driving force for some of the material to mix and why they are not mixing. We will learn a lot of physical chemistry. You probably learned in your undergraduate if you attend physical chemistry, what the entropy, what the enthalpy contributions to mixing. We will do a quick review in the next class what the entropy and enthalpy are and how they could contribute to polymer mixing. We're going to do, the ultimate goal is to help understand if you mix a polymer, a solvent, or a polymer with an alpha, will it mix or not? It's a very important question and a very practical question when you want to engineer a plastic product. If they don't mix, then you have large phase separation. Area, you have a large aggregate of one polymer, the other is the second polymer you're trying to make them mix. And this typically causes a degradation in device property or your mechanical property, which is a lot of time unfavorable for your end application. So people do a lot of different ways to try to make things mix. So we're going to go through what controls, what dictates the polymer mixing or not, and why. And we will learn entropy is always the one guy always being very positive, optimistic, always like say, hey, buddy, don't fight, let's get together, let's be good friends. So entropy also always favors mixing. We will learn that, although there is just a large degree of mixing, good or not mixing. We also have the enthalpy, which is another parameter that is interesting because enthalpy is a little bit tricky. Enthalpy means what's the heat exchange when you mix two. It could be going all kind of spectrum from very like to promote to dislike to discourage mixing. So we're going to go through that. A good way to describe it is given by, again, the famous person I talked about a couple times, Flory-Huggins. P.J. Flory and Huggins come together to describe a parameter called a chi parameter. And that is very important in the polymer physics, determines how your material will likely mix or not. The higher the chi, the less likely they will mix. So we're going to talk about that as well. With those knowledge, then next step is we're going to talk about how you can construct a phase diagram, which is probably most useful things from this class is at what temperature your polymer or whatever blend is going to mix, when, at what temperature or volume fraction they will not mix. We're going to go into the detail how to construct a phase diagram based on enthalpy and entropy. Okay? And throughout the text, we will learn also learn one thing quickly is about what is it called? Osmotic pressure. And what is unique about osmotic pressure is it can use to measure solvent quality in your material as well as the molecular weight. Okay? So we're going to insert osmotic pressure part into this discussion. And then we will finish the lecture talks about an overview of how everything comes together. We're going to introduce one last concept is a solubility parameter, how solubility parameter can be relevant to chi parameter, how you can look up solubility parameter in a polymer handbook, and how you can use their knowledges to help you better design your material. That's roughly the game plan. We're going to have about 6 to 8 classes on that. Again, we're going to follow the similar format. We're going to have some homework in the middle of the lecture. And there will be a quick test too for the second half of the, particularly the relevant to the solution property, okay? Any question for this part? If not, then we're going to dive into a new chapter in next lecture. So for you, it will be helpful. You start to reading the technologist textbook. It is very well written. And the next part is everything, I think, included in chapter 7 about polymer solution property. Okay? If no more questions, let's conclude today's class. If you can hand your test to me, that will be great. I'll put them in an archive. All right, perfect. We still didn't see Chandler, huh? Anyone know what's going on with Chandler? Okay. I'd better reach out to him. Thanks, David. Thanks, everybody.